Somewhere above you tonight, a cloud of gas is collapsing into a brand new star, the way it has for longer than anyone alive can remember. It feels eternal, automatic, guaranteed. It is not. Astronomers who reconstruct our galaxies past the way detectives reconstruct a crime scene have found something unsettling. Star birth here reached its peak billions of years before the first human existed, and it has been quietly declining ever since, with less raw material available for every new generation of stars that forms. Tonight, we trace exactly how scientists caught this ancient slowdown in the act, what is actually left in the tank, and what that slow, patient countdown means for every star still waiting to be born, including, whether we like it or not, our own sun. If stories like this help your mind unwind, liking the video and subscribing is a small way to keep more of them coming your way, and it genuinely helps more than you might expect. Settle back and let your body relax. In 3, 2, 1, liftoff. Somewhere above Mount Wilson tonight, in the direction of the constellation Orion, a cloud of gas, roughly 1,300 light-years away, is doing exactly what it was doing when Walter Baade first climbed that mountain to look through a telescope, and exactly what it was doing long before that. Deep inside that cloud, gravity is winning a slow, patient argument against pressure, folding a knot of hydrogen in on itself, squeezing it tighter and hotter with every passing century. The knot becomes a dense, dark core, invisible in ordinary light, glowing faintly only in infrared. The core becomes what astronomers call a protostar, a swollen, unfinished thing, still pulling in gas from the cloud around it, still too cool and too diffuse to count as a true star. Only after a long, uneven adolescence, a phase that can itself stretch across millions of years, does the pressure and temperature at its center finally climb high enough to ignite steady nuclear fusion, and only then does it settle down and begin to shine the way our own sun shines, quietly, for billions of years to come. Nobody has ever watched one star complete that whole journey from beginning to end. The whole process unfolds across hundreds of thousands of years, far too slow for any human eye or any human life to track from its first flicker to its final ignition. But astronomers have photographed this particular nursery, the one we call the Orion Nebula, so many times, in so much detail, that we can describe almost exactly what is happening inside it, even though every photograph is really just one frozen frame pulled from a film that runs far too slowly for any of us to ever watch play out. This is the strange trick that starlight plays on all of us. Because star formation is so slow, and because it has been going on somewhere in this galaxy for essentially the entire span of human history and every era that came before it, the night sky feels less like an event and more like a fixed backdrop. People have been looking up at that same pale band of light stretching across the darkness for as long as people have existed to look. Ancient Greek watchers pictured it as spilled milk spattered across the heavens, which is where the word galaxy itself comes from. Along the Silk Road, in ancient China, it was known as the Silver River, a wide, quiet current flowing overhead. In parts of Polynesia, sailors treated that same band as a kind of highway, a fixed marker they could steer by across open ocean, precisely because it never seemed to move or change from one voyage to the next. Every one of those cultures, separated by oceans and centuries, agreed on one thing without ever comparing notes. Whatever that pale river of light actually was, it was permanent, a fixed feature of the sky, no more likely to change than the ground underfoot. Someone lying on their back in a field 100 years ago, or 500 years ago, long before telescopes existed at all, saw roughly the same scattering of stars you would see tonight, and it looked, on any given night, exactly like it had looked the night before, and the night before that. There is real comfort in that steadiness. It is one of the reasons a clear night sky has always felt like such a dependable, unhurried thing to sit beneath, the one part of the world that never seems to rearrange itself while you are not looking. But steadiness, measured on a human timescale, is a very different thing from permanence, measured on a galactic one, and the two get confused far more often than they should. To understand why, it helps to step back from any single nebula and take in the whole structure it belongs to. The Milky Way is a flattened, spiraling disk of stars roughly 100,000 light-years across, thickened at the center into a dense central bulge and thinning out toward its edges into sweeping arms of gas and starlight. Our solar system sits well out from that center, tucked inside one of those spiral arms, more suburb than downtown, drifting along with everything else in a slow, wide orbit around the galactic core. Astronomers still argue over the precise star count because so much of the galaxy is hidden behind thick, dark lanes of dust that block ordinary starlight the way fog blocks a highway. But the honest range runs from about 100 billion stars on the low end to as many as 400 billion on the high end. If a number like that feels abstract, imagine every kernel of corn grown across the farmland of Iowa, Illinois, Nebraska, and Kansas combined in one ordinary growing season, and you would still need to multiply that entire harvest several times over just to reach the low end of that estimate. This is why, on a clear night, away from city lights, the pale river, the ancient Chinese and Polynesian navigators once described, does not look like a scattering of individual points at all. It looks like a cloudy band spilling across the sky, because what you are actually seeing is the combined, blurred together glow of hundreds of billions of stars, so numerous and so distant that your eye can no longer tell them apart, the same way a crowd stops looking like individual people once it grows large enough and far enough away. The Milky Way is not just big. It is big in a way that swallows any comparison you try to throw at it, which is exactly why a single glowing nursery like the one in Orion can feel, from where we sit, like the whole story of star birth, when it is really just one lit window in a house with hundreds of billions of rooms. There is a second, less obvious problem hiding inside all of this, one that has quietly frustrated astronomers for longer than the star formation puzzle itself. We are trying to map and measure a structure from deep inside it, with no way to step outside for a wider view. Picture trying to sketch an accurate map of a forest while standing among the trees, blindfolded by fog in every direction more than a few miles out. That, essentially, is the position every Milky Way astronomer has always worked from. Thick lanes of interstellar dust, scattered through the galactic disk, block ordinary visible light almost completely once you look more than a few thousand light-years toward the crowded galactic center, which is one reason it took until well into the 20th century for astronomers to even settle on how many spiral arms the Milky Way actually has, or to agree on roughly where our solar system sits within them. Only by turning to infrared light and radio waves, both of which pass through dust far more easily than visible light does, have astronomers gradually pieced together a workable map of our own galaxy's shape, essentially reconstructing the house from the inside, one hidden hallway at a time, without ever being able to walk outside and photograph the whole building at once. And yet, across that entire structure, hundreds of billions of stars, spanning a disk 100,000 light-years wide, the actual pace of new star birth is almost startlingly modest. Astronomers measure it the way you might measure rainfall across an entire country from just a handful of gauges, not by counting individual newborn stars directly, most of which are hidden behind dust or simply too faint and too far away to see, but by tallying up the glow of hot, young, newly formed stars and the infrared light radiating off the dust clouds those young stars are still embedded in, then working backward to estimate how much raw gas must be getting converted into starlight to produce that glow. Space telescopes built specifically to see in infrared light have spent years scanning the galactic plane inch by inch this way, cataloging tens of thousands of individual star-forming clumps, each one a small contribution to a running galaxy-wide total. The most careful recent estimates, cross-checked using several genuinely independent methods, put the Milky Way's star formation rate at about 1.65 solar masses of gas turning into stars every year, meaning roughly 1 2/3 times the mass of our own Sun, converted into new starlight, galaxy-wide, in an average 12 months. Because most stars that form are smaller than the Sun, red dwarfs especially, being by far the most common kind of star in the galaxy, that modest figure works out to something like 6 or 7 new stars across the entire Milky Way in an average year. Picture the number of babies born in a single small American town in a single year, and you are picturing roughly the same scale of event, just scattered across 100,000 light years, instead of a few square miles of Main Street and farmland. It is a strange kind of intimacy, tucked inside all that vastness, a birth rate you could almost track on your fingers, happening inside a structure too large for any human mind to properly picture. That number, small as it sounds, took the better part of a century to pin down with any real confidence, and for a long stretch of that time, it did not even agree with what theory predicted, which turned it into one of the more stubborn puzzles in galactic astronomy. If you calculate how much raw star-forming gas fills the Milky Way, and then estimate how quickly a cloud that dense and that massive ought to collapse under its own gravity, left to itself, the math points to a galaxy that should be forming new stars at a furious pace, dramatically higher, well over 100 times higher than what any telescope ever actually recorded. For decades, astronomers proposed one explanation after another to close that gap. Perhaps strong magnetic fields threading through the gas were holding the clouds together against collapse, slowing everything down. Perhaps turbulence, the same kind of chaotic churning you would see in boiling water, was constantly stirring the gas apart before it could gather into anything dense enough to ignite. Perhaps newly formed massive stars were blasting out enough radiation and stellar wind to push back against their own birth clouds, choking off further star formation nearby almost as soon as it began. Each idea captured a piece of the truth, but tested carefully against real observations, each one kept running into the same wall, explaining the full gap. This way required magnetic fields far stronger, and turbulence far more constant and widespread than anything astronomers could actually detect out in the galaxy's star-forming clouds. The theories were not wrong, exactly. They were simply incomplete, and for nearly 50 years, the discrepancy sat there, unresolved, a genuine embarrassment for a field that prided itself on being able to explain exactly this kind of thing with confidence. It was not even a problem unique to our own galaxy. When astronomers pointed the same kind of calculation at other nearby spiral galaxies, similar in size and shape to our own, the same stubborn gap showed up again and again, which at least confirmed that nobody had simply made a careless mistake measuring the Milky Way in particular. Whatever was holding star formation back, it appeared to be something built into the basic physics of how galaxies like ours behave, not a fluke of our own cosmic neighborhood. The gap was finally closed, in large part only in 2022, when a team of astronomers took a much closer look at what those star-forming clouds are actually made of. It turns out the heavier elements scattered through interstellar gas, elements forged inside earlier generations of stars and blown back out into space when those stars died, change how astronomers calculate a cloud's true mass and change how efficiently that gas actually turns into stars once turbulence and magnetic fields are properly accounted for, correct for those effects, and the wildly over-predicted rate falls back in line, almost neatly, with what telescopes have been quietly showing all along. It is worth sitting with what that really means. Even measuring how fast the Milky Way makes new stars today, right now, in our own moment, took the combined effort of multiple generations of astronomers, and was not fully understood until extremely recently, well within living memory. So, it is fair to ask a much harder question. If pinning down today's rate was that difficult, how could anyone possibly know whether that rate is unusually high or unusually low compared to any other point across this galaxy's long history? A single measurement, however precise, is really just a snapshot, and a snapshot cannot tell you anything about a trend. To know whether star birth in this galaxy is climbing, falling, or holding roughly steady, you would need something to compare today against, some kind of record stretching back across a meaningful slice of galactic time. And there is an obvious problem with that. Nobody had a working telescope 4 billion years ago, or 400 million years ago, or even 4,000 years ago. Every photograph of the sky ever taken covers, at most, the last couple of centuries, an eye blink set against a galaxy that has existed for roughly 13 billion years. And yet, remarkably, that record does exist. It has existed the entire time, written into the stars themselves, waiting for somebody to realize it was even there to be read at all. Not a written record, nothing so simple as a diary or a ledger, but something closer to growth rings inside a very old tree, patient and physical, encoded not in ink, but in the actual color, brightness, and chemical makeup of the stars scattered around us in every direction. Cutting into a tree kills it, of course, which is not much use to anyone studying a still-living galaxy. What the Milky Way needed instead was someone willing to look at the living tree itself closely enough and long enough to figure out how to read those rings without ever cutting into the trunk at all. The person who first managed exactly that was not a young prodigy with the newest equipment money could buy. He was a middle-aged astronomer working under a disadvantage that, through a strange accident of wartime history, turned into the greatest observing advantage of his career. His name was Walter Baade, and by the time this particular story really begins, he had already spent more than 2 decades near the top of his field. Born in a small town in the Westphalia region of Germany, he studied mathematics, physics, and astronomy at the universities of Münster and Göttingen, earned his doctorate, and spent the 1920s working at the Hamburg Observatory, developing a reputation as an unusually careful, patient observer, the kind of astronomer other astronomers trusted with the most difficult targets. Along the way, he had already made a real mark on the field, discovering an asteroid in 1920 that crossed the orbits of the giant outer planets, and later working alongside the physicist Fritz Zwicky, helping to coin and define an entirely new term for the most violent kind of stellar death, the supernova. In 1931, hungry for a bigger telescope than Europe could offer him, he crossed the Atlantic to join the staff of Mount Wilson Observatory in the mountains above Los Angeles. home at the time to the largest, most powerful telescope anywhere on Earth, the 100-inch Hooker telescope, a mirror wide enough to gather more starlight than any instrument built before it. Observing there was not the comfortable, climate-controlled work it can be today. Astronomers rode up a narrow mountain road to an elevation of roughly a mile, worked through long cold nights inside an unheated dome, and captured their images not on digital sensors, but on large glass photographic plates, each one requiring careful handling, precise guiding of the telescope by hand across hours of exposure, and a practiced, almost meditative patience, since a single mistake or a single passing cloud could ruin an entire night's work in an instant. Bardet had a reputation, even among his exacting colleagues, as one of the most careful and disciplined observers ever to work at that telescope. He intended, by his own account, to eventually apply for American citizenship. Somewhere along the way, in the ordinary business of settling into a new country, the paperwork was lost, and Bade, absorbed in his work, never quite got around to sorting it out. It was a small, almost forgettable administrative loose end. It was about to matter a great deal. Then the world changed around him. After the attack on Pearl Harbor pulled the United States into World War II, life at Mount Wilson shifted almost overnight. Many of Bardet's American colleagues were pulled away into classified, war-related research, developing optics and instruments for the military effort, work that consumed most of their working hours for years. Bardet, still technically a German citizen because of that unresolved paperwork, was classified as an enemy alien and barred entirely from any of that classified work. On paper, it was a professional sidelining, a mark of quiet suspicion placed on a man who had lived and worked in the United States for a decade already. In practice, it left him with something almost nobody else on that mountain still had: uninterrupted, nearly exclusive access to the great telescope, night after night, while the observatory around him steadily emptied out. And the war handed him a second, even stranger gift on top of the first. As a precaution against possible air raids, the city of Los Angeles imposed strict blackout conditions, dimming streetlights, storefronts, and the general electric glow that normally washed out the fainter stars over Mount Wilson from below. For anyone trying to coax fine detail out of a faint, distant smear of starlight, a darker sky is everything, and the sky over the observatory, for a handful of wartime years, grew darker than it had been in a very long time, and darker than it would ever be again once the lights of the city came back on for good. Los Angeles in those years was a growing city, its own glow already bright enough on ordinary nights to wash out the faintest stars over Mount Wilson, and every wartime blackout order, meant purely as protection against enemy aircraft, quietly handed the observatory back a version of the night sky that earlier astronomers, working before the city's lights had spread so far, would have recognized far more easily than we would today. Bade, with the mountain nearly to himself and the city below finally quiet, pointed the Hooker telescope toward the Andromeda galaxy, the nearest large galaxy to our own, and began taking long, patient exposures of its central bulge, the dense, glowing core that every previous astronomer, including Edwin Hubble himself, had only ever managed to capture as a smooth, structureless haze, too crowded and too faint for any telescope before this one to pick apart. Night after night. In 1944, Bardet did something nobody had managed before him. He resolved that haze into individual points of light, separating out actual, distinct stars within Andromeda's crowded core for the first time in the history of astronomy. It was an extraordinary technical achievement in its own right, the product of a once-in-a-generation dark sky, a world-class instrument, and an astronomer with the discipline and patience to take full advantage of both. And it would go on, in the years that followed, to reshape more than just the study of stellar populations. That same run of wartime observations eventually led Bade to recognize that there were actually two distinct kinds of a special, predictable class of star, called a Cepheid variable, a discovery that forced astronomers to essentially double their previous estimate of the size and age of the entire visible universe. But the true significance of what he had done first became clear much closer to home, the moment he actually sat down and studied the stars he had just uncovered in Andromeda's core. The stars crowded into Andromeda's core did not look anything like the stars scattered through its sweeping outer arms. The ones in the core glowed with a distinctly reddish cast and behaved in every measurable way like the ancient stars found inside globular clusters, tight ball-shaped swarms of many thousands, sometimes millions of stars that orbit slowly around the outskirts of galaxies, like satellites, some of them older than the galaxy's own spiral disk. Omega Centauri, the brightest globular cluster visible from Earth and a favorite target for stargazers across the American South, is exactly this kind of ancient swarm, a tightly packed ball of old, reddish stars that has been quietly orbiting the Milky Way for most of the galaxy's entire history. Roughly 150 of these globular clusters are known to orbit our own galaxy today, scattered around it in a loose, spherical halo, each one essentially a fossilized snapshot of the same ancient stellar population Bade first identified at Andromeda. The ones out in the spiral arms, by contrast, tended to burn bluer and hotter, and were consistently found scattered alongside glowing clouds of gas where new stars are actively being born. The same kind of cloud sitting right now inside the Orion Nebula, or inside the loose, sparkling cluster known as the Pleiades, easily visible to the naked eye on a clear autumn night. Bade had stumbled onto two genuinely different generations of stars, occupying the very same galaxy, and he gave them names that astronomers still use without a second thought today. The young, blue, gas-rich stars scattered through the spiral arms he called Population 1. The old, red, tightly clustered stars crowded into the core and scattered through the outer halo he called Population 2. It is worth understanding exactly why that distinction mattered so much, because it is the seed of everything the rest of this story is built on. A star's color and its chemistry are not random accidents. They are a record. Every element heavier than hydrogen and helium in the language astronomers use counts as a metal, and almost none of it existed at all in the earliest years after the galaxy first came together. Those heavier elements, the carbon, oxygen, iron, and everything else that eventually goes into building rocky planets, and, eventually, people get forged one generation of stars at a time, cooked inside stellar cores through nuclear fusion, then scattered back out into the surrounding gas when those stars finally die, often in the kind of violent supernova explosion Bade himself had helped name a decade earlier. Bright, blue, metal-rich stars form out of gas that has already been enriched, seasoned, by several of these earlier generations. A star like that is, almost by definition, a relatively recent arrival, built from recycled material, one link further down a very long chain. Old, reddish, metal-poor stars, on the other hand, formed long ago out of a galaxy's original, largely unprocessed gas, before many earlier generations of stars had lived and died to enrich that gas at all. Bade had shown without fully grasping the size of what he had just opened up, that you could look at a single star, examine its color and its chemistry, and learn something surprisingly specific about roughly when it was born. He made this discovery looking outward toward Andromeda, a separate galaxy 2.5 million light-years away. But the same principle applies just as well turned inward, toward our own galaxy, toward the hundreds of billions of stars scattered around our own solar system in every direction. Every one of those stars, whether it burns blue-white inside a spiral arm or glows a faint ancient red out in the galactic halo, carries some version of the same birth certificate. Bade first learned to read in 1944. In the decades since, astronomers have gotten dramatically better at reading it, not just sorting stars into two broad categories, young or old, the way Bade first did, but pulling out something far more precise, individual ages, measured star by star, across millions upon millions of stars at once. Using instruments Bade himself never lived to see, spacecraft and survey telescopes that did not exist, yet even at the end of his own long career at Mount Wilson, he had shown, with a single painstaking wartime achievement, that the sky was not simply full of stars. It was full of dates, hidden in plain sight, encoded in ordinary starlight, waiting for anyone patient enough to learn the alphabet. Which raises the real question this video is built around. If a single star can reveal roughly when it was born, what happens once you have precise ages for millions of them scattered across the entire disk of the Milky Way, plotted out not as two rough categories, but as a continuous, detailed timeline stretching back across the galaxy's entire 13 billion year history? What does this galaxy's actual, detailed birth record look like once you finally know how to read it in full? And what does it reveal about the 6 or 7 stars still being born here tonight, against everything that came before them? Sorting stars into two broad families, young or old, was an extraordinary leap for its time, but it was still only a beginning, and for decades afterward, it was about as far as anyone could push the idea. Astronomers who came after Bade refined the picture in small ways, adding a few more subtle gradations here and there, but the fundamental limitation never really went away. Doing better meant knowing far more about each star than color alone could tell you. Its exact distance, its true brightness once that distance was accounted for, and its precise chemical fingerprint, gathered not for a few hundred stars in one corner of the sky, but for staggering numbers of stars at once, scattered across the entire disk of the galaxy. No telescope of that era, however carefully handled, could manage a task on that scale, and for the better part of the 20th century, nobody seriously expected one ever would. What eventually made it possible was not a bigger mirror or a darker sky, the two advantages that had carried astronomy forward for so long. It was a spacecraft built to do one job, over and over, with a patience no human observer sitting at an eyepiece night after night could ever match. Measure the exact position of well over 1 billion stars, repeatedly, for years on end, until their motions across the sky became measurable. That spacecraft is called Gaia, launched by the European Space Agency in late 2013 and named, fittingly enough, after the ancient Greek goddess of the Earth. Gaia does not orbit our planet the way a weather satellite or the International Space Station does. It sits far out beyond the Moon at a quiet, gravitationally stable spot roughly 1 million miles from Earth, where the pull of the Earth and the pull of the Sun balance out just enough to let a spacecraft hover there with a minimum of fuel, slowly spinning sweeping its twin telescopes across almost the entire sky over and over as the months and years pass. From that vantage point, Gaia has spent more than a decade watching for the tiny, almost imperceptible shift in a star's apparent position as our solar system moves through space, the same effect that makes a nearby telephone pole appear to slide past a distant mountain when you look out a moving car window. Except here, the telephone pole is a star, the mountain is the rest of the galaxy, and the shift being measured is smaller than the width of a human hair viewed from across a city. That shift, measured with almost unbelievable precision, reveals a star's true distance. Combine distance with how bright a star actually appears from Earth, and you can calculate exactly how much light it is truly putting out. Its real, intrinsic brightness, not just how bright it happens to look from wherever we are sitting. Gaia has done this for more than 1 billion stars, building what astronomers sometimes describe as a census of the galaxy, a working map not just of where stars sit in the sky, but of how far away each one truly is and how brightly it truly shines. No mission before it had ever attempted anything close to this scale of precision applied to this many stars, and the resulting catalogue now underpins an enormous share of everything modern astronomers know about the structure of our own galaxy. This particular discovery included, on its own, though, even a map that detailed could not answer the question Bade's discovery had first raised. Position and brightness will tell you a great deal about a star. They will not, by themselves, tell you its age, and for that, one more piece of the puzzle was still missing. For that, astronomers needed a second kind of information entirely: a star's chemical makeup, the specific mix of elements burning inside it, gathered not from Gaia's cameras, but from ground-based telescopes equipped to split starlight apart into its component colors and read the fine dark lines hidden within it. Each line a fingerprint left by a particular element, the same basic principle that lets a chemist identify what is burning in a flame just by studying the color of the light it gives off. One of the largest efforts to gather this kind of data comes from a wide-field spectroscopic survey based in China, a telescope built specifically to point at thousands of stars at once, each one fed into the instrument through its own individual optical fiber, splitting and recording thousands of separate rainbows of starlight in a single night's work. Over the years, that single survey has patiently built up detailed chemical readings for millions of stars scattered across the galaxy, a library of stellar fingerprints large enough that almost any star an astronomer wanted to study for this project was already sitting somewhere inside it. Layer that chemical information on top of Gaia's precise distances and brightness measurements, and something remarkable becomes possible. You are no longer just sorting stars into Bade's two broad piles. You can, in principle, assign an individual, fairly precise age to almost any ordinary star you choose to study, the way a geologist might read the age of a rock formation from the layers pressed into it. There was still one obstacle left, and it turned out to be the most important one. Most stars, for most of their lives, sit in a very stable, very ordinary phase, quietly fusing hydrogen into helium in their cores, the same phase our own sun is in right now, and during that long, stable stretch, a star's outward brightness and temperature stay frustratingly similar across a huge range of possible ages. A 5-billion-year-old sun-like star and an 8-billion-year-old sun-like star can look almost identical from the outside, which makes them nearly useless as precise clocks, no matter how good your instruments are. It would be a little like trying to guess a candle's total burn time by glancing at it once, part way through, while the flame still looks steady and unchanged. Astronomers needed a different kind of star altogether, one caught in a brief, telltale transition rather than a long, stable plateau. They found it in what are called subgiant stars. A subgiant is a star that has just finished burning the hydrogen fuel at its very center, so that fusion has shifted outward into a thin shell surrounding an inert core, a short-lived, unstable arrangement that a star passes through quickly on its way toward becoming a much larger, brighter giant. During that narrow window, a star's brightness and surface temperature change together in a very particular, very tightly constrained way, one that depends almost entirely on the star's mass, and therefore, once its chemical makeup is factored in on how long it has already been alive. Catch a star in that specific, fleeting phase, measure it carefully, and you have found something close to a genuine cosmic hourglass, one whose sand you can still see falling, rather than a jar you can only judge as roughly full or roughly empty. It is a brief phase, astronomically speaking, which is exactly what makes it so useful. A star only spends a small fraction of its total lifetime as a subgiant, which means that wherever you find one, you have caught it at a moment that pins down its age with unusual confidence, rather than leaving you guessing across billions of years. The trade-off, of course, is scarcity. Because the phase is so brief, subgiants make up only a small fraction of any random sample of stars, which is exactly why a project like this one needed a spacecraft capable of surveying more than 1 billion stars in the first place, simply to gather enough of these rare, telltale specimens to build a statistically solid picture of the whole galaxy's history, rather than a scattering of individual anecdotes. In 2022, two astronomers working at the Max Planck Institute for Astronomy in Germany, Maoshang Xiang and Hans-Walter Rix, put all of these pieces together at a scale nobody had previously attempted. Combining Gaia's positions and brightness measurements with chemical readings gathered from that same Chinese spectroscopic survey, Xiang and Rix identified roughly 250,000 subgiant stars scattered across the Milky Way's disk. Stars caught in exactly that brief, telltale transitional phase, and calculated an individual age for each one, typically accurate to within a small margin of error, a level of precision that would have seemed like science fiction to an astronomer working in Baade's era. Rather than publishing a handful of case studies, Xiang and Rix sorted their entire sample by age and plotted the results as a single continuous curve, a graph tracing how quickly the Milky Way was forming stars at every point across nearly the whole of cosmic history, decade by decade in some sense, rather than era by era. For the first time, astronomers were not simply describing the galaxy as young stars here, old stars there. They had, in effect, produced a detailed, dated timeline of when the Milky Way actually built its stars, generation by generation, stretching back across almost the entire history of the galaxy itself. Picture that timeline stretched out like a long shoreline, with the present day standing at one end and the galaxy's earliest years standing at the other, and imagine walking backward along it, watching the number of new stars being born at each point rise and fall as you go. For the stretch nearest to us, the shoreline is calm, almost flat, matching the modest handful of stars we know the Milky Way still produces today. Walk far enough back, though, and the shoreline changes completely, rising into something closer to a single towering dune, far taller than anything found anywhere else along the walk. What that timeline showed surprised even the researchers who built it, and it overturned an assumption that had quietly stood for decades. Before this study, most astronomers pictured the Milky Way's disk assembling itself gradually, patiently, over most of the galaxy's history, with no single moment standing out as obviously more important than any other. The new timeline said otherwise. It pointed to one specific, unmistakable peak, sitting far closer to the beginning of the galaxy's story than anyone had confidently placed it before. The oldest stars in the sample, the very first entries in the Milky Way's timeline, turned out to be considerably older than most astronomers had expected. Star formation in what is now called the thick disk, an earlier, puffier layer of stars that surrounds and cushions the thinner, flatter disk our own Sun belongs to, began roughly 13 billion years ago, a mere 800 million years after the Big Bang itself, when the universe as a whole was still in its infancy. To put that in perspective, the Milky Way was already forging stars while most of the rest of the cosmos was still assembling its very first generation of galaxies, back when the very first stars anywhere were only just beginning to switch on. The Milky Way we know today, spiral arms and all, did not exist yet in any recognizable form. What existed was something rougher and less organized, clumps and streams of gas and young stars still settling into the shape that would eventually become a galaxy at all, gathering itself together. The way a snowball rolled downhill, gathers mass and shape as it goes. Astronomers sometimes call this period galactic assembly, a fittingly plain, workmanlike term for a process that involved smaller clumps of gas and young stars merging together over and over, each merger adding mass and eventually rotation until the whole structure began to settle into something resembling an actual disk rather than a loose, disorganized swarm. It is worth remembering that none of this early history was visible or even guessable from Bardé's era. Sorting stars by color, the way he did looking at Andromeda in 1944, could tell you a star was old. It could never have told you that the galaxy's oldest stars were already forming a mere 800 million years after the beginning of time itself, an answer that required exactly the kind of star-by-star precision that would not exist for another 3/4 of a century. This was not a gentle, gradual beginning. The early data showed a burst of activity, a rapid buildup of stars, in a relatively short span of cosmic time, before something even more dramatic came along and pushed the pace higher still. Roughly 2 billion years into that early stretch, placing the event at somewhere around 11 billion years ago, the young Milky Way collided with another galaxy, a substantial one, not one of the faint, wispy dwarfs that occasionally brush past us today, but a genuine collision partner carrying, by some estimates, gas, stars, and dark matter together amounting to something on the order of 50 billion times the mass of our own Sun. Its total mass in gas, stars, and dark matter combined dwarfed anything the Milky Way has run into since, which is exactly why its fingerprints are still so easy to find, even after all this time. For decades, evidence of this ancient encounter sat hidden in plain sight, far through the orbits and chemistry of stars in the Milky Way's inner halo, indistinguishable from ordinary galactic debris, until Gaia's precision finally made it possible to tell the difference. Astronomers eventually gave this vanished galaxy an unexpectedly playful name, and the story of how they found it is worth pausing on. Working from Gaia's newly released catalogue of stellar motions in 2018, an astronomer named Vasily Belokurov, along with colleagues at the University of Cambridge, plotted the velocities of thousands of nearby stars on a chart, tracking not just where each star was, but exactly how fast and in what direction it was moving through the Milky Way at that instant. Most stars, tracing the Milky Way's calm, orderly rotation, clustered together in a fairly ordinary, unremarkable pattern. But a distinct group of stars did something else entirely. Plotted the same way, their velocities traced out a long, narrow, curved shape, stretched out across the chart in a way that looked unmistakably, to everyone who saw it, like a sausage. By Belokhurov's own account, the shape simply jumped out at them the moment the data went up on the screen, impossible to miss, and, once seen, impossible to unsee. The name stuck almost immediately, half as a joke and half out of sheer convenience, and astronomers still call the vanished galaxy the Sausage Galaxy today, occasionally alongside a second, more formal name borrowed from Greek mythology, Enceladus, a giant said to have been buried beneath the earth by Gaia herself, a small, poetic echo of the fact that this ancient collision partner now lies buried within the very structure the modern Gaia spacecraft was built to map. The collision itself would have been almost unimaginably violent, at least by the standards of anything else in this story. The Sausage Galaxy did not settle gently into orbit around the young Milky Way the way a smaller companion might. It came in on a steep, plunging path, driving nearly straight toward the center of our galaxy rather than easing in from a wide, gentle orbit. And when the two systems finally met, the smaller galaxy was torn apart within a relatively short span of cosmic time. Its stars were flung onto long, narrow, needle-like paths, hurled inward toward the galactic center and back outward again in stretched, elongated loops, orbits so distinctive that astronomers can still pick many of those same stars out individually today, more than 10 billion years later, simply by how they move. The impact left the Milky Way's own young disk shaken to its core, likely puffed up, thickened, and possibly even partially torn apart by the encounter, forcing much of it to settle and slowly rebuild itself in the collision's aftermath, the way a pond's surface has to still itself again after a heavy stone breaks through it. And as the wreckage of the Sausage Galaxy scattered through the inner regions of our own, it brought fresh gas and fresh material with it, material that appears to have poured directly into the thick disk's ongoing construction project, pushing star formation there into overdrive at precisely the moment it should have been slowing down on its own. At least 8 of the roughly 150 globular clusters known to orbit the Milky Way today are now thought to be adopted arrivals from that very collision, ancient swarms of stars that once belonged to an entirely different galaxy and have circled our own ever since, quiet monuments to an encounter that happened before the sun existed. Astronomers can still tell these adopted clusters apart from the Milky Way's own native-born clusters, even after 10 billion years of shared history, because they carry two separate, independent fingerprints of their foreign origin. Their orbits tend to be steep and elongated, echoing the same plunging path the Sausage Galaxy itself took on its way in, rather than the calmer, more settled paths typical of clusters that formed here from the beginning. And their chemistry carries a subtly different signature, a slightly different balance of heavier elements than clusters born from the Milky Way's own gas, a residue of having formed inside a separate galaxy with its own separate chemical history before ever falling into ours. Between the telltale orbits and the telltale chemistry, the wreckage of an ancient galaxy that no longer technically exists can still be picked out, star by star and cluster by cluster, more than 10 billion years after the fact. a level of forensic detail that would have seemed like pure fantasy to Bade, working with nothing but a telescope, a photographic plate, and a wartime blackout less than 100 years earlier. Much of the drama of that encounter would have played out not in stars colliding with other stars, which almost never happens, even in the most violent galactic collisions, given how much empty space separates one star from the next, but in gas colliding with gas. The Sausage Galaxy carried its own substantial reservoir of hydrogen along with it, and as the smaller galaxy's outer regions were stripped away by the Milky Way's gravity, that gas did not simply vanish or drift off into empty space. Much of it slammed into gas already sitting inside the young Milky Way, compressing, shock heating, and tumbling inward toward the thickening disk, exactly the kind of violent squeeze that pushes ordinary interstellar gas past the tipping point into forming stars. Seen from far outside, if any observer had existed to see it, the encounter would have looked less like two solid objects crashing together and more like two storm systems colliding, each one dragging its own trailing streamers of gas and dust, the streamers tangling, compressing, and lighting up with new star birth, exactly where the collision pressure ran highest. That collision left behind a visible legacy that stock footage of ordinary spiral galaxies can only hint at. Astronomers now believe the encounter helped fashion both the Milky Way's dense central bulge and much of its surrounding stellar halo, reshaping the raw material of an unfinished galaxy into structures that are still recognizably there tonight, sitting quietly overhead, visible in any wide photograph of our galaxy's crowded center. Under that kind of pressure, the thick disk's star-forming days moved at a pace that dwarfs anything happening in the galaxy today. Where the modern Milky Way manages something like 6 or 7 new stars a year, the early thick disk, fed by its own reserves and freshly enriched by the wreckage of its fallen neighbor, was assembling stars fast enough to build an entire layer of the galaxy, one that still today holds a meaningful share of the Milky Way's oldest surviving stars, in a window of cosmic time far shorter than the multi-billion-year stretch that followed it. Picture a river during spring flood, swollen with melting snow, carrying more water past a given point in a few frantic weeks than it will carry across the rest of the entire year combined, before settling back into its ordinary, modest, steady channel once the flood passes and the snow is gone. The thick disk's construction was that flood, brief and overwhelming. What has followed ever since has looked, at least on the surface, much more like the ordinary channel. That pace could not continue indefinitely. In any case, gas, however abundant, is a finite resource, and by around 6 billion years after the Big Bang, meaning roughly 7.5 to 8 billion years ago, the thick disk's raw material was largely spent. Star formation there slowed sharply, and the galaxy's attention shifted to a new, flatter, more orderly layer of stars settling into place closer to the galactic plane. The thin disk, the layer that our own sun and our own solar system would eventually be born into several billion years later still. It would be tempting, at this point, to assume the rest of the story is simple. A spectacular, ancient boom, a single dramatic collision, a long, gradual decline ever since, arriving neatly at the modest handful of stars the Milky Way produces each year today. Before following that thread any further, it is worth pausing on just how much this single study changed. Before Shang and Rix published their timeline, most descriptions of the Milky Way's early history treated the thick disk's formation as a slow, gradual process, unfolding gently over billions of years. without any obvious external trigger. The sausage collision and the precisely dated evidence tying it to a sudden spike in star birth replaced that gentle picture with something closer to an origin story, with an actual inciting incident, a specific, violent encounter that can be pointed to, roughly dated, and connected directly to the shape of the galaxy we live in today. It also quietly resolved a nagging discomfort among astronomers who study nearby, similar spiral galaxies, since many of the Milky Way's neighbors show signs of having gone through comparable early collisions of their own. Rather than being some strange local exception, our galaxy's violent youth increasingly looks like an ordinary chapter in how a spiral galaxy of this size is generally built. One more piece of evidence: the galaxies grow the way most complicated things grow, not in a single smooth line, but through a handful of formative, disruptive events separated by long, quieter stretches of ordinary business. The timeline Zhang and Rix uncovered does show the broad shape, an early surge followed by an overall decline stretched across billions of years. But a broad shape is not the same thing as a smooth one, and when astronomers looked closely at the more recent portion of that same record, the last few billion years rather than the first, they found something that did not fit a simple, steady decline at all. The sausage galaxy was an enormous, one-time event, the kind of collision that only happens once in a galaxy's history, a wound so large it left a permanent scar on the Milky Way's structure. It was not, it turns out, the last time something crashed through the Milky Way's disk and left a mark on how many stars we make. Long after the thick disk finished its work, and the thin disk began its slower, quieter build-up, something smaller has been doing a scaled-down version of the same thing, again and again and again, right up to the present day. Whatever it is, it has been doing this recently enough, and often enough, that its fingerprints sit near the very end of the timeline, close enough to the present that the story it tells reaches almost all the way to the handful of stars still forming in the Orion Nebula tonight. Unlike the sausage, whose collision happened once and finished billions of years before the Earth even existed, this repeat visitor appears to still be nearby, its most recent pass close enough in time that some astronomers now wonder whether the Milky Way, at this very moment, might be in the early stages of yet another one of these episodes, quietly gathering steam somewhere overhead as you listen to this, identifying what that repeat visitor actually is, tracing exactly when each of its visits happened, and understanding what its return trips reveal about the Milky Way's more recent habits, is where this story goes next. The repeat visitor has a name, and astronomers have actually known about it for longer than they have understood what it was doing to us. It is called the Sagittarius Dwarf Galaxy, a small, faint smudge of stars first identified in 1994 by three astronomers, Rodrigo Ibata, Gerard Gilmore, and Mike Irwin, who stumbled across it almost by accident while surveying the crowded, star-choked region toward the center of our own galaxy. They had not set out looking for a new galaxy at all. They were studying the motion of stars in the Milky Way's central bulge, ordinary bulge stars that should have been moving in roughly predictable ways, when a cluster of stars showed up moving differently, drifting together at a speed and in a direction that matched nothing nearby, nothing that belonged to the bulge they thought they were studying. Follow-up observations, gathering more stars and pinning down their distances more carefully, confirmed what that strange, coordinated motion implied, ruling out simpler explanations one by one, until only a single answer remained standing. Hidden almost directly behind the crowded, dust-choked heart of the Milky Way, on the far side of the galactic center from where we sit, drowned out by the glow of billions of foreground stars and the same obscuring dust that had already complicated so much of this story, sat an entire separate galaxy, one of the closest neighbors the Milky Way has, that nobody had ever managed to pick out before. The discovery was published in the journal Nature that same year, and it briefly made Sagittarius the nearest known galaxy to our own, a title it would go on to hold for the better part of a decade before later more contested discoveries muddied the ranking. The Sagittarius dwarf galaxy is nothing like the sausage, and it is worth noting it is not even the only smaller companion currently interacting with the Milky Way in this way. The large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere and easily mistaken for detached patches of the Milky Way itself, are believed to be undergoing a milder version of the same slow gravitational tug-of-war, their own gas reserves, already showing signs of being pulled and disturbed by our galaxy's much larger mass. Sagittarius, though, remains the clearest, best dated example of the pattern, precisely because its passages have been close enough and violent enough to leave a mark that Gaia's precision could actually recover. Where the sausage was a single massive, one-time collision that tore itself apart and finished its work more than 10 billion years ago, Sagittarius is small, faint, and still very much intact, at least for now, caught in a long, slow, repeating orbit around the Milky Way that has been tightening for billions of years, the way a stone on a string spirals gradually closer to your hand the longer you swing it. Each time that orbit carries Sagittarius through the crowded disk of the Milky Way, the encounter strips away a little more of it, pulling loose streams of stars that now stretch most of the way around our galaxy, faint trails still marking the paths of countless earlier passages, visible today only through painstaking surveys, able to pick out the handful of stars belonging to Sagittarius from the far larger crowd of ordinary Milky Way stars surrounding them. Astronomers studying that stream have effectively been able to trace the dwarf galaxy's entire recent orbital history simply by mapping where its abandoned stars now sit, a trail of breadcrumbs left behind by a galaxy still slowly being consumed, one loop of the spiral at a time. Unlike the sausage, Sagittarius does not appear to have brought much gas along with it. Careful searchers have failed to find any significant reservoir of hydrogen gas associated with the dwarf galaxy today, which means that whatever influence it has had on the Milky Way's star formation, it has not worked the same way the sausage did, by dumping in a large supply of fresh raw material. Sagittarius has been affecting us almost entirely through gravity alone, its own mass tugging and disturbing the Milky Way's already existing gas each time it plunges through, rather than adding new fuel of its own, a quieter, more repetitive kind of influence than the single overwhelming shove the sausage delivered. That distinction matters more than it might first seem. Picture a heavy freight train rumbling past a row of houses late at night, never touching any of them directly, but passing close enough, night after night across many separate trips, that the ground trembles just enough to rattle a little dust loose from the shelves inside, dust that had been sitting undisturbed since the last train came through. No new dust arrives with any of those trains. Whatever settles back onto those shelves between visits was already inside the house the whole time, simply waiting for the next passing vibration to shake it loose again. That, roughly, is what repeated close passages from a smaller galaxy can do to the gas already sitting inside a much larger one, compressing clouds that were otherwise drifting along quietly, nudging them past the threshold needed to collapse and begin forming stars, without needing to supply a single new atom of hydrogen to do it. Knowing that Sagittarius existed, and knowing roughly how its orbit has behaved, astronomers had long suspected it must be leaving some kind of mark on the Milky Way's star-forming history. Confirming it and dating it precisely required exactly the same tool that had already rewritten the story of the ancient thick disk earlier in this account: the Gaia spacecraft and the enormous, precise catalogue of stellar positions, brightness, and motion it has spent more than a decade building. In 2020, an astronomer named Tomás Ruiz Lara, working at the Instituto de Astrofísica de Canarias in Spain, led a team that set out to reconstruct, in careful detail, the recent star-forming history of the region of the galaxy immediately around our own Sun, a sphere roughly 6,500 light-years across. Rather than looking at the ancient history the way the earlier study of the thick disk had, Ruiz Lara and his colleagues focused close to home and close to the present, comparing the colors, brightness, and distances of enormous numbers of nearby stars, drawn straight from Gaia's catalogue, against detailed models of how stars of different ages ought to look. It is worth appreciating how different this approach was from Bardé's original method, decades earlier, where Bardé had sorted stars into two broad piles by eye, working from a handful of photographic plates exposed one painstaking night at a time. Ruiz Lara's team fed enormous numbers of individual stars into computer models capable of testing thousands of possible star formation histories against the observed data at once, searching for whichever combination best explained the actual mixture of colors and brightnesses Gaia had recorded, a task that would have taken a human observer many lifetimes to attempt by hand. What emerged from that comparison was not a smooth, gradually declining curve. It was a curve with three distinct, sharply defined spikes rising out of it. Three separate episodes, when star formation in our own corner of the galaxy surged noticeably above the ordinary background rate before settling back down again. Ruiz Lara's team was able to date these spikes with real precision, one centered around 5.7 billion years ago, a second around 1.9 billion years ago, and a third around 1 billion years ago. Lined up against existing models of Sagittarius's orbit, the match was almost immediate. Those three dates correspond closely to the 3 times astronomers believe Sagittarius has plunged through the disk of the Milky Way, dragging its gravity across our galaxy's own gas each time and leaving a burst of new starbirth in its wake. The Sagittarius dwarf galaxy, it turned out, had been quietly setting off a chain of star-forming events across billions of years, 3 separate times, each one traceable, each one datable, each one written into the ages of stars sitting in our own galactic backyard. There is a detail buried inside that first burst, the one centered around 5.7 billion years ago, that is worth sitting with for a moment. Our own Sun is roughly 4.6 billion years old, meaning it formed sometime after that first burst had already peaked and begun to fade, but still within the same broad, extended episode of enhanced star formation. That burst appears to have touched off an episode the data suggests lasted the better part of 1 billion years from start to finish. The timing is suggestive rather than proven, close enough to be genuinely intriguing without being close enough to call it confirmed, and Ruiz Lara himself has been careful to describe it as a possibility rather than a settled fact. Astronomers are, understandably, cautious about drawing too straight a line between one specific ancient collision and one specific ordinary star. since countless stars formed across that same billion-year stretch for all sorts of reasons, having nothing to do with Sagittarius at all. Still, the coincidence raises an almost dizzying thought, offered here with all the appropriate caution attached. It is not impossible that the Sun, the solar system, and everything that eventually grew from it, including every person who has ever lived, owes its existence, at least in part, to the gravitational disturbance of a small, faint galaxy hidden behind the crowded center of our own, colliding with the Milky Way's disk long before Earth existed in any form at all. The three bursts were not identical to one another, and the differences between them turned out to matter almost as much as their timing, since a decline that speaks in fading echoes tells a different snee than one that simply falls in a straight, unbroken line. Each episode was progressively weaker than the one before it. The 5.7 billion-year-old burst, the strongest and longest of the three. The 1.9 billion-year-old burst, noticeably fainter, and the one centered around 1 billion years ago, fainter still. This fits naturally with what has been happening to Sagittarius itself the entire time. Every time it plunges through the Milky Way's disk, the encounter strips away more of its stars and whatever gas it once carried, leaving a smaller, more depleted galaxy behind for the next pass. Its total mass shrinking a little further with each completed orbit. A galaxy that keeps losing mass every time it swings through should, all else being equal, disturb the Milky Way's gas a little less forcefully with each repeat visit. And that is almost exactly the pattern the data shows. A fading signal from a fading messenger. The story does not stop at 3 bursts, and this is the part of the record that reaches closest to tonight. Buried in the same data, Ruiz-Lara's team found a hint of a possible 4th episode, fainter and less certain than the other 3, but appearing to span roughly the last 70 million years. Remarkably recent by the standards of everything else in this story. Later research, published a few years afterward and using its own independent analysis of the same general region of sky, went further still, reporting an increase in star-forming activity that could be confidently traced back across roughly the last 10 million years. A blink of an eye set against a 13 billion-year-old galaxy, and considerably more confident than Ruiz-Lara's original tentative hint had been. 2 separate research teams, working with somewhat different techniques and arriving at somewhat different precise numbers, nonetheless agreed on the same broad conclusion, drawn independently from the same crowded stretch of sky. Something has been nudging star formation upward again, quite recently, and whatever it is, has not yet finished its work. Sagittarius, according to the orbital models astronomers currently favor, may have swept through the disk again quite recently, within roughly the last few 100 million years, and by some estimates, may still be close enough to the disk today to still be nudging it. Confirming that connection with the same confidence Ruiz-Lara's team brought to the 3 older, more clearly defined bursts will likely require another decade or more of Gaia data and an even larger, more precisely dated sample of young, recently formed stars than astronomers currently have in hand, since the youngest, most recent star-forming episodes are, almost by definition, the hardest of all to separate cleanly from the ordinary, ongoing background rate of star birth happening everywhere else in the disk at the same time. If that is correct, it would mean the Milky Way may currently be sitting inside the early, quiet stages of a 4th star-forming episode right now, one that has not yet had time to build to the strength of its 3 predecessors, adding one more layer of uncertainty to a rate that, as established earlier, was never an easy number to pin down in the first place. Step back from the individual bursts, and a larger, more complicated shape starts to come into view, one that neither the ancient collision nor the recent Sagittarius episodes can explain entirely on their own. Astronomers who study galaxies broadly enough to compare thousands of them at once sort spiral galaxies into rough categories based on how actively they are still forming stars. Categories that show up clearly once you plot enough galaxies against each other on the same chart. Galaxies that are still churning out stars vigorously, their disks bright with young, blue stars and glowing nurseries, are usually called blue, star-forming galaxies. Galaxies that have used up or lost most of their star-forming gas and have settled into a long, quiet retirement of old, reddish stars with little new birth left to show are called red and dead, or quiescent. In between those two extremes sits a smaller, less clearly defined population, galaxies that are neither vigorously forming stars nor finished doing so, caught somewhere in the slow, gradual process of transitioning from one state to the other. Astronomers, with a fondness for tidy visual metaphors, call this in-between category the Green Valley, after where such galaxies tend to cluster on a chart that plots galaxy color against brightness, a name that has stuck in the scientific literature for years now, despite, or perhaps because of, how vividly it captures the idea of a galaxy caught partway between two very different futures. The Milky Way, based on its current, modest star formation rate and the overall trajectory the Xiang and Rick's timeline revealed, is generally classified by astronomers as sitting inside that green valley today, alongside its neighbor Andromeda, neither the vigorous blue spiral it once was, back during the thick disk's furious early construction, nor the quiet red galaxy it may eventually become, once whatever gas remains is finally exhausted for good. Being in the Green Valley does not tell you, on its own, which direction a galaxy is actually heading, and this is where honest uncertainty has to enter the story. A galaxy generally lands in that middle category for one of two very different reasons. It might be a star-forming galaxy on its way out, gradually losing the fuel that once powered vigorous star birth, drifting slowly and permanently toward the quiet, red side of the chart. Or it might simply be a star-forming galaxy having an unusually quiet stretch, the kind of temporary lull that can happen for all sorts of reasons, before picking back up again once fresh gas arrives or an old reservoir gets stirred back into motion, the way Sagittarius appears to have done 3 times already. Distinguishing between those two possibilities, a slow, permanent decline versus a temporary lull inside a longer, bumpier story, requires knowing something that remains genuinely difficult to measure: how much gas is still flowing into the Milky Way from beyond its own disk, and whether that inflow can keep pace with everything currently being consumed. Here, the numbers get genuinely uncomfortable, at least at first glance. Astronomers can estimate how much star-forming gas the Milky Way currently holds in reserve, largely by measuring radio and infrared light given off by cold clouds of hydrogen scattered through the disk, and compare that figure against how quickly the galaxy is using it up through ordinary star birth, the kind of careful bookkeeping that only became possible once surveys like these had mapped the disk in real detail. For spiral galaxies broadly similar to our own, that comparison typically produces what astronomers call a depletion time, the length of time it would take to exhaust the entire remaining gas supply if nothing new ever flowed in to replace it. For galaxies like the Milky Way, that depletion time generally comes out to somewhere around 1 to 2 billion years, a figure that sounds alarmingly short set against a 13-billion-year-old galaxy, until you remember that the Milky Way is not a sealed container. gas does not simply vanish once it is used. Massive young stars burn through their fuel quickly and explode as supernovae, blasting much of their material back out into the surrounding disk in enormous, expanding shells of hot gas, visible in telescope images as glowing, shredded clouds long after the star itself is gone, where that material cools, mixes back in with the undisturbed gas around it, and eventually becomes available to form stars all over again. A slow, continuous recycling process astronomers sometimes call the galactic fountain, gas rising, cooling, and raining back down in a cycle that can repeat many times before that material is ever permanently lost to the thin, near-empty space between galaxies. On top of that internal recycling, fresh gas appears to be falling into the Milky Way from well beyond its own disk as well, drawn in from the thin, largely invisible material that drifts through the space between galaxies and from smaller companion systems, including, as we have already seen, the depleted remains of Sagittarius itself. Whether that combination of recycling and fresh inflow is enough to fully offset 1 to 2 billion years of steady consumption indefinitely is a genuinely open question, and honest scientists say so plainly rather than pretending otherwise. Some research suggests the inflow is currently falling short, that the Milky Way is taking in less fresh gas than it is using up, which would mean the Green Valley classification reflects a real, if slow, one-way drift toward eventual quiescence, the kind of gradual fade already visible in the very oldest, quietest galaxies astronomers can observe elsewhere in the universe. Other work suggests the balance is closer to even than it looks, particularly once the recycling from the galactic fountain and periodic disturbances like Sagittarius are properly accounted for, which would make the Milky Way's current lull look less like a one-way ending and more like an ordinary, unremarkable dip in a long, uneven career, the kind of quiet stretch a galaxy might pass through several times before its story is finally finished. Both possibilities remain on the table. What is not in serious dispute is the broader trend line itself. The fact that today's modest 6 or 7 stars a year sits nowhere close to the pace the thick disk once managed, and that the galaxy's overall trajectory, bursts and lulls included, points generally downward across cosmic time, even if the exact slope of that downward line, and whether it flattens out or keeps falling, remains a subject of active, ongoing research rather than settled fact. It would be easy, hearing all of this, to assume the Milky Way's story is a strange, singular case, a galaxy with an unusually complicated, unusually violent history that happens to be ours simply because we live inside it. Zoom out far enough, though, past our own galaxy entirely, and the same basic shape reappears at a scale too large for any one collision or any one dwarf galaxy to explain. Astronomers have spent decades pointing telescopes at galaxies scattered across enormous distances, and because light takes time to travel, looking far away also means looking far back in time, catching galaxies as they appeared billions of years before the present. Stitch enough of those distant snapshots together at every distance and every era, and you can reconstruct something even larger than the Milky Way's own timeline, a star formation history for the observable universe as a whole. That universal timeline traces a shape strikingly similar to the one hidden inside our own galaxy's disk. Star birth across the cosmos as a whole was not always as modest as it is today. It rose steadily in the young universe, reached a broad peak somewhere around 10 billion years ago, an era astronomers have taken to calling cosmic noon, when galaxies everywhere, on average, were forging new stars at a pace many times higher than anything happening in the universe today, and has been declining ever since, gradually but unmistakably, falling to roughly a tenth of its peak rate by the time you reach the present day. The Milky Way's own ancient boom, driven by the sausage collision roughly 11 billion years ago, falls almost exactly within that same broad, universal peak, less a strange local coincidence than a single, well-documented example of something that appears to have been happening to galaxies everywhere at roughly the same time, ours included. Ordinary, in that sense, despite everything dramatic about how it happened to us specifically. Whatever conditions allowed the early universe to forge stars so much more efficiently than it does now, gas that was denser, more abundant, and more easily available for galaxies of every size to draw on, our own galaxy's history turns out to be one thread inside a far larger tapestry rather than an isolated exception. Why the universe as a whole has been slowing down this way remains, remarkably, an open question, and recent work on the subject is refreshingly candid about that fact. Researchers can measure the decline itself with real confidence, mapping it across billions of years of cosmic history using thousands of distant galaxies, explaining exactly why it has unfolded the way it has, whether the available gas across the universe is simply running out, whether galaxies are becoming less efficient at turning the gas they do have into stars, or whether some combination of both is responsible, remains a genuinely active area of study rather than a settled conclusion, with astronomers still openly debating the underlying cause in research published as recently as this year. What is not in doubt is the direction. Across individual galaxies and across the observable universe as a whole, the peak era of star formation is behind us, not ahead of us, and every galaxy still forming stars today, our own included, is doing so on the declining side of that curve. Put all of it together, and the picture the Milky Way's own record tells stops looking like a single, simple story and starts looking like something closer to a long, uneven career, rather than a straight line pointed toward an ending. An explosive, violent youth, most of the galaxy's oldest stars built in a matter of a few billion years under the pressure of a single overwhelming collision. A long, gradual settling afterward, punctuated 3 separate times by a smaller, fading companion still stubbornly making its rounds, each visit leaving a fainter mark than the one before it. A possible 4th episode, faint and unfinished, that may be unfolding right now, somewhere in the disk overhead, too recent and too subtle to have fully declared itself in the data yet. And underneath all of it, a slower universe-wide tide pulling galaxies everywhere, our own included, gradually toward quiet, a tide that began long before the Milky Way existed in any recognizable. The remaining question is not whether this decline is real. On that point, the evidence across every scale, from a single stellar nursery in Orion to the entire observable universe, agrees. The remaining question is what happens next. What a galaxy running on borrowed, diminishing bursts actually looks like a few billion years further down that same road, and whether anything resembling tonight's quiet, steady trickle of new starlight is likely to still be burning by the time that road runs out. A galaxy running on borrowed, diminishing bursts does not simply fade in a straight, predictable line, and the honest answer to what happens next depends on an encounter astronomers have spent more than a decade arguing about. An encounter involving the one galaxy in the night sky, large enough and close enough to actually rival our own, visible even now, on a clear enough night, as a faint, elongated smudge hanging in the constellation of the same name. Everything traced so far in this video, the ancient collision that built the thick disk, the three fainter echoes stirred up by a small, wounded companion still circling us, has been a story about the past, reconstructed carefully out of the ages and motions of stars that already exist. What comes next is a different kind of question entirely, a question about a future nobody has actually observed, pieced together instead from the careful, patient work of tracking exactly how fast and in exactly which direction our nearest large neighbor is currently moving. For most of the past 15 years, the story seemed essentially settled, though the roots of the story reach back considerably further than that. As early as 1912, an astronomer named Vesto Slipher, working at Lowell Observatory in Arizona, first measured that Andromeda's light was shifted toward the blue end of the spectrum, the telltale sign of an object moving toward an observer rather than away, making Andromeda the fastest moving object anyone had measured up to that point, and establishing, more than a century ago, that our two galaxies were approaching each other at all. What Slipher could not measure, and what remained genuinely unknown for the better part of 100 years afterward, was Andromeda's sideways motion, the piece of the puzzle that would ultimately determine whether that approach ends in a direct hit or a near miss. Slipher's original measurement, made using nothing more than a spectrograph attached to a telescope on a hill in Arizona, remains the foundation every subsequent refinement has built on, a reminder that even the most sophisticated recent calculation still rests on more than a century of accumulated, patient observation. In 2012, astronomers at the Space Telescope Science Institute, using years of patient observations from the Hubble Space Telescope, measured something that had never been pinned down with real confidence before: exactly how the Andromeda Galaxy is moving sideways across our sky, not just toward us, which was already well established through simple changes in its light, but side to side as well, a motion so slight it had eluded every previous attempt to capture it. The sideways motion turned out to be remarkably small, a genuine surprise, which meant Andromeda was heading almost directly at us, on what looked very much like a collision course, rather than on a path that might carry it past us at a safer distance. Combine that finding with Andromeda's already well-measured approach, speed, roughly 250,000 miles per hour, closing the gap between our two galaxies a little more with every passing year, and the conclusion seemed to follow naturally. Astronomers projected a first close pass in roughly 3,750,000,000 years, tidal forces beginning to warp and stretch both galaxies' disks by around 4 billion years from now, drawing long, glowing streamers of stars out of each galaxy, the way the ancient sausage collision once did to the young Milky Way, streamers that would themselves have been visible had anyone been watching from far enough away, as two once separate pinwheels of light slowly reaching toward each other across the dark, followed by one or two further passes before the two systems finally settled into a single merged galaxy, somewhere around 6 billion years from now. For years, this timeline appeared in documentaries and planetarium shows as something close to certain, a fixed, inevitable date on the galaxy's calendar, illustrated in vivid animations, showing Andromeda swelling larger and larger in an imagined future night sky before the two spirals finally tangled together. Certainty of that kind is a rare thing in astronomy, and it did not survive contact with better data. In 2025, An astronomer named Till Sawala at the University of Helsinki led a team that revisited the entire question using measurements that simply had not existed in 2012. Newer, far more precise data from both Hubble and the Gaia spacecraft, the same spacecraft whose work has already reshaped so much of this story. Rather than treating Andromeda's future path as a simple, two-body problem between it and the Milky Way alone, Sawala's team accounted for the gravitational tug of two additional, smaller galaxies that earlier work had mostly set aside: the Triangulum Galaxy, a companion of Andromeda, and the Large Magellanic Cloud, a companion of our own galaxy, one of the very same interacting neighbors mentioned earlier in this video. Each of those smaller galaxies carries enough mass to nudge the larger orbital dance around it just slightly, and slight nudges, compounded across billions of years, can add up to genuinely different outcomes. Folding in 22 separate variables, each carrying its own margin of uncertainty, distance, mass, sideways motion, and more, and running the numbers forward 100,000 separate times to see how differently small changes in starting conditions could play out. Sawala's team arrived at a very different answer than the one that had stood for over a decade. Rather than a near certainty, the odds of a direct head-on collision between the Milky Way and Andromeda within the next 10 billion years came out to something close to 50%, essentially a coin flip. In roughly half of the simulated futures, the two galaxies collided and merged, much as the earlier work had predicted. In the other half, gravity nudged them just enough that they swept past one another instead, near misses rather than direct hits, drifting on afterward as two separate galaxies still bound loosely together, but never actually merging within the time frame considered. It is worth sitting for a moment with what that 50% actually means, because it is easy to hear and move past too quickly. This is not scientists throwing up their hands and admitting they know nothing. It is the opposite, a far more careful, far better resourced calculation than the one that came before it, one that openly reports its own uncertainty rather than hiding it behind a single confident headline. Exactly the kind of honest, self-correcting process that let earlier segments of this video replace a decade of assumptions about the Milky Way's own early history with a precisely dated timeline. Sawala himself has described predicting the long-term future of galaxies this way as being a little like trying to throw a tennis ball at a target from an enormous distance, while the wind keeps shifting slightly with every gust. Small uncertainties in speed and direction, compounding over billions of years into a genuinely open question rather than a settled outcome. More data is expected soon. New measurements from Gaia, arriving this very year, should sharpen the picture further, refining exactly how fast and in precisely which direction Andromeda is truly moving, potentially tipping that 50% meaningfully one way or the other, for the first time since Sawala's team published their findings. For now, though, the honest answer to whether the Milky Way and Andromeda will ever collide is neither yes nor no. It is a coin that has not yet finished its fall. Part of what makes this particular prediction so difficult is a property that shows up throughout physics whenever you try to project any orbiting system far enough into the future. Small errors in today's measurements, a fraction of a percent uncertainty in how fast Andromeda is truly moving sideways, or exactly how much mass the Large Magellanic Cloud actually carries, do not simply stay small as you run the calculation forward. Over a few 100 million years, they barely matter. Over several billion, they compound, nudging the simulated path a little further off course with every additional orbit, not unlike a ship's compass reading just a hair off true north, a discrepancy too small to notice leaving harbor, but one that lands the ship on an entirely different shore after weeks spent following that same slightly mistaken heading. That is precisely why Sawala's team needed 100,000 separate simulated futures rather than a single confident calculation, running the same starting uncertainties forward again and again to see the full spread of where they could plausibly lead, rather than pretending any single run could capture the truth on its own. Suppose, for a moment, that it lands on collision, the scenario that once seemed guaranteed and now looks merely likely. What would that actually mean for everything traced earlier in this video? A close encounter between two large, gas-bearing spiral galaxies would very likely reignite star formation dramatically, at least for a while, gravity compressing whatever gas the Milky Way still has left, far more forcefully than any small companion like Sagittarius ever managed on its own. The way squeezing a sponge harder pushes out water that gentler pressure never could, water that had been sitting quietly, unnoticed, for longer than anyone was watching. Astronomers who model these kinds of major mergers generally expect a genuine burst, new stars flaring to life across both galaxies in numbers far beyond anything happening tonight, a final, spectacular chapter, rather than a quiet fade, visible, if anyone were around to see it, as entire spiral arms lighting up with new stellar nurseries, far brighter than the modest one currently glowing in Orion, the kind of sight astronomers have already photographed happening to other pairs of colliding galaxies scattered across the observable universe. Distant previews of a scene our own galaxy may or may not eventually stage for itself. That burst would not last. Bursts triggered by major mergers tend to be short-lived and self-limiting, since the massive young stars they produce burn hot, burn fast, and explode as supernovae in large numbers, flooding the merging galaxies with radiation and shock waves that heat and scatter the remaining gas faster than gravity can gather it back up. The supermassive black holes at the heart of each galaxy, including the one presently sitting at the center of our own, hidden behind the same crowded, dust-choked bulge mentioned earlier in this account, would likely become far more active during this period as well, feeding on gas stirred up by the encounter and pouring out enough additional energy in the form of intense radiation and powerful outflowing winds to help finish the job of shutting star formation down for good, sweeping much of the remaining gas out of the merging galaxies entirely, rather than leaving it to simply cool and recollect. What would eventually settle out of all that chaos, astronomers generally agree, is a single, large, smooth elliptical galaxy, its spiral arms gone entirely, its gas mostly spent or blown away, a stellar population aging quietly from that point forward, with little left to replace it, the kind of galaxy that would show up in any telescope survey as a calm, featureless glow rather than the structured pinwheel we know tonight, its long history of bursts and quiet stretches alike smoothed over into a single, unremarkable shape. This hypothetical merged galaxy already has an informal name, coined half in earnest and half as a joke, the way Sagittarius's shattered stellar stream earned its own nickname earlier in this story. Astronomers sometimes call it Milky Way, a name that has stuck in casual conversation among researchers, even though, as of this recording, there remains a genuine chance it will never actually be needed, the coin still turning somewhere overhead. its outcome not due to settle for billions of years yet. Now, suppose the coin lands the other way, and the two galaxies simply pass by one another without ever fully merging within the next 10 billion years, gravity bending both paths just enough to avoid the direct hit. The way two cars approaching an intersection from different directions can pass through within moments of each other without ever touching, so long as their timing and their angles line up just right, a matter of a few feet or a few seconds, deciding the entire outcome. In that version of events, the Milky Way's future looks considerably less dramatic, but not necessarily less certain in its overall direction. Without a major collision to compress its gas and force a final burst, the galaxy would likely continue along something closer to the path already traced earlier in this video. An uneven, punctuated decline, occasional smaller disturbances like the ones Sagittarius has already triggered 3 times, each one weaker than the last, layered over a gradually thinning reserve of star-forming material that nothing currently on the horizon appears likely to fully replenish. Both branches, the dramatic collision and the quiet near miss, ultimately point in a broadly similar direction over long enough timescales. One version reaches a quiet, aging elliptical galaxy sooner by way of one last dramatic burst. The other reaches something recognizably similar more slowly, without that final flourish, simply by continuing to spend down a gas supply that was never going to refill itself indefinitely. Whether by collision or by continued gradual attrition, the galaxy this video opened with, still quietly forming a handful of new stars in the Orion Nebula tonight, is not expected to look anything like this forever. On any branch of that 50-50 coin, a conclusion that holds regardless of which way Andromeda's uncertain trajectory eventually resolves. Here is where the honest scale of all this deserves a pause, because it is easy, listening to numbers like 10 billion years, to lose track of what actually falls within a time frame that matters to any of us. Compare all of this uncertainty about Andromeda to something considerably more settled, the future of our own sun. The sun is roughly 4.6 billion years old, and it has, by the careful reckoning of solar physicists studying stars of similar mass and composition, somewhere in the neighborhood of 5 billion years left before it exhausts the hydrogen fuel in its core and begins the slow transformation into a red giant, swelling outward, according to current models, far enough to engulf Mercury, to engulf Venus, and quite possibly to reach all the way out to Earth itself. Notice what that means, set against everything else discussed in this video. The sun's own ending arrives comfortably before either branch of the Andromeda question has fully played out, whether that branch involves a dramatic collision or a quiet, uneventful passing, meaning whatever else the far future holds for this galaxy. The sun itself will already have moved into its own final chapter well before any of it is settled, one way or the other. Sawala, discussing his own findings, has pointed out something worth carrying forward from all of this. Whatever eventually happens between the Milky Way and Andromeda, the ending of our own sun is the more certain, and in many ways the more consequential, event for any planet still orbiting it, a plain, grounding fact that has nothing to do with coin flips or shifting odds and everything to do with the ordinary, well-understood physics of how a star like ours spends its fuel. A galaxy merger, should it happen at all, would reshape the sky dramatically without necessarily threatening the sun or Earth directly, since actual collisions between individual stars during a galaxy merger remain exceedingly rare. the space between stars simply too vast for that. Each star and its neighbors separated by distances that dwarf the stars themselves many times over. The sun's own aging, by contrast, is not a coin flip. It is closer to a certainty already written into the physics of how every star like it behaves, a process astronomers can model with confidence by studying countless other sun-like stars scattered across every stage of that same life cycle, some younger, some already well along the same path our own star will eventually follow. Which brings this account back, finally, to where it began, and to the quiet, unglamorous handful of stars the Milky Way is still managing to produce tonight. Everything traced across this video, the ancient, furious burst that built the thick disk under the pressure of a collision with a galaxy now known only as the Sausage, the three fainter, more recent echoes, stirred up by a small, wounded companion still circling us today, the uncertain, coin-flip future waiting somewhere between now and a possible encounter with Andromeda. All of it belongs to a single, continuous story, one far longer than any single human life, and far longer even than the whole of human history laid end to end. From the earliest cave paintings to the telescope currently orbiting 1,000,000 miles from Earth and gathering the very data this account has leaned on so heavily. It began roughly 13 billion years ago in a burst of star formation so intense it built an entire layer of the galaxy in what amounts, on cosmic timescales, to barely more than a moment. It has been slowing unevenly ever since, not because anything broke, but because a finite reservoir of gas has been doing exactly what a finite reservoir of anything eventually does when it is drawn down faster than it is replaced, spending itself down a little further with every generation of stars that forms and burns and eventually dies, leaving slightly less behind for whichever generation comes next. There is a particular kind of comfort available in a story like this one, though it takes a moment to notice, and it has nothing to do with pretending the decline is not real or dressing up a genuine, measurable slowdown as something other than what it is, the way a person might be tempted to do with any long, slow change they would rather not look at directly. Consider, for a moment, what it means to inherit a garden someone else spent a lifetime planting, arriving too late to have done any of that early digging and shaping yourself, too late to have chosen where the first trees went in, or which seeds got planted along which fence line, but early enough to still walk through it in bloom, to still smell what is growing, to still sit in whatever shade the older trees have grown tall enough to offer. After decades, nobody currently alive was around to witness. Nobody arriving at that garden in its later, quieter years is somehow cheated out of something more real than what the original gardener experienced. The blossoms are no less fragrant for having been planted by someone else's hands. In an earlier season, neither owner is asked to feel guilty for missing. A garden past its wildest, most explosive early growth is not a lesser garden. It is simply a garden further along in the only kind of story any garden ever tells, one of planting, growth, a long productive middle stretch, and an eventual, gradual quieting that does not erase anything that came before it, any more than a quiet autumn afternoon erases the spring that came before it. Every star sitting overhead tonight, ordinary or otherwise, was planted by a version of this galaxy that no longer exists in the same form today, an ancient, furious, gas-rich Milky Way that spent itself building the very structure that would, billions of years later, produce a small, unremarkable, entirely sufficient yellow star, and around that star, a modest blue planet, and on that planet, eventually, someone lying quietly in the dark, listening to a story about where the stars overhead actually came from, warm and comfortable, with nowhere else they need to be tonight. None of this requires believing the Milky Way was building toward us specifically, some grand design aimed at any particular outcome, humanity, or the sun, or Earth, as the point of the whole exercise. The evidence gathered across this video points the other way entirely, toward an old, ordinary galaxy behaving the way old, ordinary galaxies behave, shaped by an ancient collision it did not choose, disturbed periodically by a small companion still slowly being consumed, facing an uncertain future with another, larger neighbor that may or may not ever arrive. There was no plan, no target, no design aimed at any single planet or any single species capable of eventually asking these questions, no more than there was a plan behind which particular raindrop in a passing storm happens to land first, or which particular ember in a dying fire happens to catch a stray breath of air and flare back up for a while longer than the rest. And yet, somewhere inside that unremarkable, physically explicable process, gas turning into starlight, starlight into heavier elements, elements into planets, one particular planet turned out to be quiet and stable enough, for long enough, for something to grow on it capable of eventually building a telescope and pointing that telescope outward and asking where any of it came from in the first place. That outcome required no design. It only required time, an ordinary galaxy's worth of billions of years, spent the way galaxies of this size and history generally spend them, and enough patience on our part, arriving as late as we have, to finally learn how to read the record it left behind, patiently enough to sort stars into two families the way Bard first did, patiently enough to eventually date individual bursts to within a few 100 million years, patiently enough to run a calculation 100,000 times rather than settling for one confident guess. Somewhere back near the beginning of this account, mention was made of the ancient Greeks, who looked at that same pale band overhead and pictured spilled milk, and of sailors in Polynesia, who steered by it precisely because it never seemed to change, trusting a light they could not explain simply because it had never once let them down. None of them knew what they were actually looking at. They could not have known, watching that band of light with nothing more than their own eyes, that it represented the accumulated glow of hundreds of billions of individual stars, most of them born in a handful of specific, datable episodes stretching back across 13 billion years, some ancient and violent, some faint and recent, a handful, even, still smoldering into existence tonight. They simply knew it was there, night after night, steady enough to trust, useful enough to navigate by, beautiful enough to build stories around, long before anyone had a word for a galaxy, let alone a way to measure how fast one galaxy's star-making habits had changed across billions of years. In a strange way, they were not entirely wrong to treat it as something permanent, even though, as this whole account has tried to show, permanence was never quite the right word for it. A process this slow, this vast, this gradual, can look exactly like permanence from the inside of a single human lifetime, or a single human civilization, without actually being permanent at all. And both things, the steadiness and the slow, ongoing change underneath it, have been true at the very same time for as long as anyone has been alive to notice either one. Being born late in a story like that, well past the galaxy's most productive years, arriving during what amounts to a long, quiet, gradually fading afternoon rather than the bright, furious morning of 13 billion years ago does not make the story any less real or any less worth paying attention to while it continues. A fading process is still, for as long as it keeps fading, a process, still active, still doing what it has always done, simply doing a little less of it with each passing billion years than it once did. The garden is still blooming. There are still a handful of new stars catching fire in Orion tonight, doing, patiently, exactly what stars have always done, entirely indifferent to whether anyone happens to be listening. Tonight, at least for a little while longer, someone is. Sleep well. Somewhere above, ancient gas is still quietly becoming starlight.